All right, what's going on, everybody? Today we're going to be doing median of two sorted arrays. So let's get into it. So we're given two sorted arrays, nums1 and nums2 of size m and size n, respectively. They want us to return the median of the two sorted arrays with an overall runtime complexity that is big O of log m plus n. So basically, they want us to write an algorithm that returns the median of these two arrays if they were combined in logarithmic time. So let's go ahead and look at some input output and see why this is extremely hard. So we have nums1 here, and that's just going to be 1, 3. We have nums2, it's going to be 2. So imagine if we were to merge these arrays, we would get 1, 2, 3, and then the median, as you remember from statistics, it's just the middle value in a list of sorted values. So the median here is going to just be 2 for an odd sized array. For an even sized array, because nums1 is size 2, nums2 is size 2. It's going to give us a combined array of size 4. That's going to be the average of the middle two elements. So it would just be 2.5 for this example. So the reason why this is so hard is because it's extremely trivial. If we were, both of these arrays are sorted, right? We know that. If we were to just combine them, this would be really easy because then we could literally just take those middle two values or middle one value, depending whether their array's odd or even, and just return that, and that would be the median, and we could call it a day. But combining them is going to, we can't combine them with a faster time complexity than linear, right? Because we're going to have to, in the worst case, like look at every element in both arrays. Um, so that's going to be time complexity that's linear with respect to the size of those arrays. But that's way too slow, right? Because they want a logarithmic big O of log m plus n time complexity. So basically, um, if you were asked something like this on an interview, um, you know, if the array is sorted and you're doing some kind of searching for a value in the array, then you can oftentimes use binary search, right? So, and that's exactly what we're going to do for this problem. So let's get into the whiteboarding for the algorithm. So let's go ahead and I'm just going to write some, uh, come up with some values for some arrays to use as an example. So we'll say nums1. Let's just pretend nums1 is 1, 2, 3, 5. And then let's pretend nums2 is, let's just say, 4, 6, 7, 8, 10, 11. So notice, basically, in terms of global values we're going to need for our algorithm, the first one that we want is just the total. So, and what I mean by total, that's like how many elements there would be in the combined array from these two arrays. So notice there's 4 elements in nums1, and then there's 6 elements in nums2. So the total would just be 10. We are also going to need half of that total to help us with some calculations in our algorithm. So half is literally just going to be the total divided by 2. So that's going to be 5, or we could just do regular integer division. Um, so if our total was like 11, it would still be, half would still be 5 here. So let's go ahead and I'm going to actually just combine these arrays because I think it helps visualize this problem, even though we're not actually going to physically be combining them in the code. It still helps to see what they look like when they're combined. So we have 2, 4, literally just going through all of these values one by one. And this is why this version would be a bad solution, because we have to literally look at every single one, every single element, right? So, but nevertheless, there's the combined array. So for binary search, first things first, we're only going to be binary searching on one of these arrays, and it's going to be the smaller of the two arrays. So we're going to want, before we do anything, we need to ensure in order for our algorithm to work, we need to ensure that nums1 is the smaller of the two arrays. So now that we have that out of the way, nums1 is the smaller array, we can basically set our pointers for our binary search. So that's going to be typical. We're going to have a left pointer at the 0 index and a right pointer at the n-1 index. And I'll call nums1, I'll give that size n, and nums2 of size, will have size m. I think that might have been the other way around in the problem statement, but nevertheless, I'm going to do it the way I'm going to do it. So this one's going to have size n, and this one will have size m. Okay, so now that we have that out of the way, we're going to want to calculate a midpoint for both arrays with each iteration of our algorithm. So each iteration of our binary search. So the way we're going to calculate the midpoint for the array we're binary searching on for the first array is actually going to be a little bit different than what you would typically do for a binary search problem. So instead of just taking the average of these indices, we're going to be taking the floor of the average of those indices. And the reason why is because it turns out we can actually go out of bounds with our midpoints, and that's going to be valid for our search algorithm because, as you can imagine, you might like exhaust elements from one of the arrays, at which point the index of your midpoint might go out of bounds, but we need to keep uh, looping at that point. So we're gonna do something special to handle those cases. But nevertheless, we need to account for negative values here, which is a little weird, but hopefully you'll see why as I continue to explain this. So, uh, and just to give an example, so like in C++, if you were to divide -1 by 2, this would basically give you zero, right, it will give you 0 because you would get something like -0.5, right? And then you truncate the decimal place. But we don't want 0, we want -1. So we're going to be taking the floor of this, like I was saying. So so to do that, we're just going to add 0 to 3. We get 3 divided by 2, 1.5, and then the floor of that will just be 1. So the second midpoint, we were going to calculate that is we want, so let me mark the midpoint for the first array. So we're basically partitioning this array. So we're going to partition it into halves, and we want, the way we're going to calculate the midpoint for this other array is we want to have the difference of elements from however many elements there are in half of the merged array for the left partition. This is going to be a constant, by the way. This half value is a constant. Um, we're basically, so we're going to take the difference, so 5 minus 2, and then we have to, or -1, sorry, and we have to subtract that again by -2 because both of these arrays are 0 indexed. So anyways, it'd be 5 minus 1 minus 2, which would be 2. So our second midpoint here will be 2, 0, 1, 2. And then notice with that calculation, we have the sum of these is equal to the number there are in the merged array. So this is good. And basically what we want to do at this point, there's going to be a comparison that we use basically to check whether or not we've found our answer and also how to proceed with our binary search. So what we're going to do is we're basically going to compare the greatest element from the left half, from the left partitions, with the smallest element from the right partitions. So in the right partitions would look something like this. Um, and this is actually, so we're going to be comparing this value to this and this value to this. And I think a better way to color code this, now that I think about it, would be to circle the ones we're comparing with the same color. So let me do that. So we're going to be comparing 2 to 8. And we basically want 2 to be less than or equal to 8. And then we want to you take the inverse of the other array. So let me get like a purple for this. So we'd want to compare 7 and 3, and we want 7 to be less than or equal to 3. When both of these conditions are true, we know that our arrays are correctly partitioned, so we can just return the result at this point, and I'll show how to do that once we get there. But notice, so while 2 is less than or equal to 8, 7 is not less than or equal to 3. So basically what that's indicating is that we have not enough elements from this first array. So we need to continue our binary search this direction and keep searching the right half of this array to extend the size of this left partition and get closer to the correct partitioning of these arrays, because we basically want all of these elements in the left partition of this array and the left partition of this array to be equal to these elements here. And notice they're not. So as you can see, we do need to extend this left partition this way and decrease the size of this one. So the way we're going to do that, let me just get the eraser. I'm going to have to erase quite a bit here. So I'm just going to erase all of this. So our midpoints are going to change. So and before I erase that, so the way you update the pointers to continue binary searching for binary searches, if we're searching to the right now, our left pointer is just going to be equal to the midpoint here plus 1. So our new left pointer will just be this, and then we can take this one away, take this away, and these can go away also. So now we can calculate our new midpoint, which is going to just be, uh, let's see, 0, 1, 2 plus 3. We take the sum of those, so 5, and then we take the floor of that divided by 2, so 2. And then to calculate our second midpoint, that's going to be let's see, half, right? Because the number of elements here in half minus the midpoint of the first array, and then minus 2 for the two zero index arrays, so 1. So our new midpoint here will be there. And then let's check out our new partition, our new left partition. So that'll be the left partitions. Right away, we can see that those elements are not the same as this, but why? We'll do that comparison. So this element is less than or equal to this one. So that's fine. But let's look at the other element. We can see that this 6 is not less than or equal to that 5. So once again, this is the same condition that we just had. We need to keep searching the right half of this array to keep trying to extend this left partition. So, and I never wrote the midpoint there, but that was 1. So now we can do basically keep searching the right half of this array. So let's go ahead and do that. So our new midpoint will basically, or our new left pointer will basically just be the midpoint plus 1 again. So our left pointer is going to go here. It's now going to be overlapping with the right pointer. And the midpoint will just be the average of those, which is just, it's going to be 3, obviously, because the left and right pointers are on the same index. So that'll be the new midpoint. And let's see, obviously our left partition is going to change now. So this is the midpoint for that one. We need to calculate the midpoint for the other one. So it'll be, let's see, 5 minus 3 minus 2. So it'll be 0. Nice and easy. So now our partition is just, we're just taking one element from that array now. So the midpoint is now there. So as you can see, we're going to do the comparison again, but notice there's no right element here anymore. So this is a edge case that we're going to handle in the code. And the way we're going to do that is, first of all, let's compare this element with this one. We can see that 5 is less than 6, so that's good, but we don't have an element here. So when our midpoint goes out of bounds in the positive direction, we're just going to treat that like, let me just get like a different color here. We're going to treat that like, we're basically going to treat this value here like positive infinity. So we'll set that to int max in C++. And then if we go out of bounds in the negative direction, we're going to set this value to negative infinity, which will be int min in C++. And the reason being is because we can, as you can see, like literally in this example, we can exhaust all the elements in these arrays, in either of these arrays, and we still need to be able to continue with the algorithm. Uh, so regardless, so we're going to treat this like positive infinity. So I'm going to get that purple out again. So again, this will be positive infinity here, and we're going to be comparing that to 4. So is 4 less than or equal to positive infinity? Yes. So at this point, both of these conditions are true. We know that we've found the correct partitioning of these arrays, so we can return the result. So the way we're going to do that is, let's see. So basically this, notice we have an even sized array, right? So we can't just return um, simply a single value. We need to take the average of two values, right? But which values? Like, how do we know which values to take? So you can see this 4 is here, like so. Um, and then the 5 would be this value, and the 6 is going to be this value. So basically, the way this is going to work is, and then we would have a positive infinity over here, but that doesn't really exist. But anyways, so we're basically going to be taking the maximum of the elements of the greatest elements from the lower partition and the minimum of these two smallest elements in the upper partition. And what that will do is basically tell us exactly which elements are right here closest to the center of the array. So once we've done that, we'll get 5 and 6, and then obviously the result there is just going to be 5.5. So that's going to be the answer to this uh, test case, and hopefully that walkthrough kind of helps give a better understanding of like what's actually going on in this algorithm, because it's a little confusing. So admittedly, so let's go back here and then code the solution now. So the first thing we're going to want to do for a code is, if you recall, we need, well, actually, before we even do that, we need to get the size, to get some variables for the size of these arrays, because that's going to help basically make our code just more concise, more readable. So, because calling nums2 dot size, nums1 dot size repeatedly gets really verbose. So we have n for the size of nums1, m for the size of nums2. I'm going to be doing that the other way around from the problem statement. So just keep that in mind. Um, the first thing we want to do after that, I guess the next thing we want to do is, but before we get into the algorithm, we have to make sure that n or nums1 dot size is less than nums2 dot size. We want nums1 to be a smaller array. If we're not binary searching on the smaller array, this algorithm's not going to work. So basically, if n is greater than m, we know that nums1 is the larger array, which is what we don't want. So what I'm going to do is I'm just going to return a recursive call to this function to swap their references. Uh, so we're going to find median sorted arrays on nums2 for the first value and then nums1 for the second value. And that'll just swap them. That handles that. So now that we're sure nums1 is the smaller array, we need to set up some variables here. So our total, that's what I was going to do. It's basically going to just be the sum of both of the sizes of the array. So n plus m. We also want the half. So that'll just be, we can just do integer division here. So total divided by 2 is totally fine. And we're also going to have a result. And remember, we can have decimal places for arrays that are even. So that result will be a double. We're also going to have left and right pointers. So left will be the first index, right will be the n-1 index on that first array. And then we are also going to need variables for those midpoints. So mid1 for the midpoint of the first array, mid2 for the midpoint of the second array. We're also going to want, it really helps us if we assign variables to those pivot values that we'll be comparing. So we'll just call the two greatest values in the left partitions of the arrays left one and left two respectively for array one for nums one and nums two. And then right will represent those lowest values in the right partition, the upper partition of nums one and nums two. So that should be all the variables there. So we can go ahead and just loop while true because we know we're always going to find a median every time. So while true, and then we're going to break when we find it. But the midpoint, the calculation, remember, we're taking the floor. It's not just the regular average. So we need to take the floor and we're going to need to cast this to a double because C++, we need that to actually give us a decimal to take the floor of. So we're going to cast it to a double and then we're going to divide by 2. So that'll give us the, let's see, did I do that right? Yeah, looks right. So that'll be the basically the midpoint for our first array. We also need to get the midpoint for the second array. So the algorithm for that is just half, which we calculated already as a global constant, half minus, let's see, that's going to be, we're going to subtracting the midpoint of the first array and then minus 2 because both of those arrays are 0 indexed. So we also need to set values for these, basically the elements we're comparing that are at the pivot points of the two arrays. So the way we're going to do that is, remember, we can go out of bounds in the negative direction for elements in the left portion of the array partition, or so the left partition of the array. We can go out of bounds in the negative direction. So we basically need to check if the index of that midpoint is less than 0, and at which point we know we've gone out of bounds. So we're going to represent that with the minimum integer in C++. And otherwise, we can literally just actually set that to the value at index mid 1. We're going to do the exact same thing here for the greatest value of the left partition for array 2. So left 2, we're going to check if mid 2 is less than 0. If so, we set that to negative infinity. Otherwise, the actual element there. And then we're going to do something else for the right. So the lowest values in the right upper portion of the upper partition of the arrays can actually go out of bounds in the positive direction. So we need to basically, and again, and remember, I say mid 1 here because the index there of the greatest value in the left partition is literally going to be at the midpoint. The lowest value in the upper partition is going to be the midpoint plus 1. So if the midpoint plus 1 is greater than or equal to n, which is the size of that array, so if it's out of bounds positively, we need to treat that. We need to simulate positive infinity with the maximum integer in C++. Otherwise, we'll set it to the actual element there, so mid 1 plus 1. And then we're going to be doing something very similar for this for right 2. So just going to paste that. So right 2, so mid 2 plus 1 greater than or equal to m, right? Because the other array size m, we simulate positive infinity. Otherwise, we just set this to the actual element there in the array. So now we can get to the conditions. So the first thing we'll do is we'll check if we've found the answer. So if we've partitioned these arrays correctly, recall that left 1 is going to be less than or equal to right 2. And we also have to check the inverse case. So left 2 needs to be less than or equal to right 1. So both of those things are true. We know we found the answer. So, but remember, there's two cases for an even-sized merged array or an odd-sized merged array. So if our merged array is even, we can check that by just taking the modulus of the total. So, so if the total mod 2 is 0, we know it's got to be even. So remember, there's something a little fancy we have to do here. So the result is going to be equal to basically we've got to, so first of all, I'm going to cast this to a double, but we've got to take the maximum of those left partition values. So left one, left two, and then that'll give us whichever one is closest to the actual pivot. That's what we need. We're not closest, but actually we want the one that's literally adjacent to the pivot point, right? So we're going to add that to the minimum value of those right partition values. So right one, right two. And notice we have infinities here potentially, but this is either going to be, if it is infinity, it's going to be negative infinity. So always going to be taking the actual value there. Likewise for this one. So we're just going to divide that by two to get that average. And then that's going to be it for that calculation. Now the other case, we know it's got to be odd size total array, right? That's the only other case here. So in that case, basically the midpoint is going to be one. It's going to be, it's not going to be the actual um, midpoint because of decimal truncation. Or I don't even know if truncation is a word, but the decimal is going to be truncated. Basically, the midpoint is going to be um, come from the right partition. So we need to take the minimum of right one and right two, and that's going to give us the mid. It's just going to be a single value, whichever is in the middle of the array for odd sized arrays. So the last thing to do here is we need to do our actual binary search, right? We haven't done that part of the algorithm. So if this isn't true, we know that either left one is greater than right two, or left two is greater than right one. So we'll check the first case that I said and here first. So if left one is greater than right two, well, what does that mean? Basically, we know that we've taken too many elements from the uh, upper half, or we have too many elements from the first array from array nums one. So we basically want to, in order to decrease the size of that left partition and continue searching for the correct pivot point, we need to move the right pointer down to the midpoint -1 to continue searching on the lower half of the array. So so that'll just be our right point is going to be set to mid one -1 to search the left half of that array. And then the other case here is if left two is greater than right one, that's just the opposite. We don't have enough elements from nums one in this case. So we need to continue searching we need to continue our binary search on the upper half of the array to find the correct pivot point. So left is going to be equal to mid one plus one. And then at the end of this, let me zoom out because I just noticed you can't see anything. Basically, we're just going to return res. That way we have something in all control paths. Also, we need to break out of the loop here once we've found the answer because we don't need to continue the algorithm anymore at that point. We just want to break out of the loop and then return the result. So this is pretty much it for the code here. So let's go ahead and run this. So let's see, we're getting a bug here. So let's go ahead and try to fix this. So let's see, nums one. Yes, so we did our order of operations incorrectly here. This parenthesis needs to be here because we want this to evaluate as a single value, and then we want to do the division. So yeah, so that should be good. So let's run this again. Sorry for the bug. So let's go ahead and submit to see our percentages and then call it a day. So let's see, we beat 72% with runtime, 51% with memory. So hopefully this video helped you understand this problem more. If it did, please leave a thumbs up and subscribe, and I'll see you guys in the next piece.